Can artificial black holes be the great filter for advanced civilizations? Where exactly will the Artemis 3 mission be landing on the moon? What's the smallest possible star? And in our Q&A Plus version, how much would a fossil from Mars cost? Answering all these questions and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Keiichi S, do protoplanetary disks form spiral arms like galaxies? Yes. There are some absolutely incredible images from the Atacama Large Millimeter Array, which now astronomers are looking at protoplanetary disks. These are disks of planet-forming material, what our own solar system probably looked like a few 100,000 to a few million years after the cloud of gas and dust started to condense down into the sun and planets. And they actually look surprisingly similar to spiral galaxies. Some don't. Some just look like they're concentric rings around a central bright core. Others, but do seem to have spiral arms. And the forces that are working in a protoplanetary disk are very similar to the ones that are working at the larger galactic scale. And so it's not surprising that you see similar features. I mean, I think the thing that's so surprising to me is how different these protoplanetary disks look from each other, that each one is this amazing individual. And now that there have been dozens of these images taken of these disks, we're starting to get a much better census of what they all look like. And some of the really interesting findings is they seem to be a lot smaller than what you would expect, that the solar system, for the size of star that we have, is actually a pretty big planetary region, that in fact the majority of protoplanetary disks are smaller than Jupiter. And so it may be that over time, we're going to find that actually a lot of planetary systems out there have planets that are a lot closer to their star than what we have in the solar system. And maybe that makes us special. So, this is an unfolding area of research. But look at these pictures. This is amazing. Basketvector, how close are they to selecting a site on the lunar South Pole? And will that be a competitive process? So we still don't know where the Artemis 3 mission is going to land on the moon, but we do know that it is going to be close to the lunar South Pole. This is this place that's incredible because you have craters that are permanently shadowed from the sun. And so we know that they have deposits of water ice in them. But where exactly are they going to land? And the answer is that we don't know. Now, at Universe Today, we have reported on the selection process many times, and they have huge AI models, computers. They are doing machine learning on lots of different categories, thinking about the amount of large rocks on the surface that could inhibit a landing, thinking about the slopes, that could you get a landslide in the area, how much sunlight they're going to be able to get, how far they're going to have to be to get to some of these permanently shadowed craters on the moon, what resources are available, what scientifically interesting places are available, how well can they communicate back with Earth. Like, there's a lot of factors at play here that they are evaluating all of these places. And I think, they're down to the dozen or so potential landing sites on the moon, but they haven't actually chosen the one. And any of those sites would be great, but they're going to be ones that'll be better than others. So right now, as I'm recording this in the end of April 2025, we don't know the exact landing site, but we will probably know it fairly soon. I wouldn't be surprised if a year from now we do know the exact landing site where the Artemis 3 mission is going to go. Paul Wilson, question from my daughter. What is the smallest size a star can be? So a main sequence star, like the sun, has a very important characteristic, which is that it has enough gravity, enough mass, so that it has an internal pressure and temperature at its core that hydrogen can be fused. This is a main sequence star. And the sun is actually a fairly large version of one of these main sequence stars. The vast majority of stars are smaller, and yet they are still fusing hydrogen into helium at their core. And they're called red dwarf stars, or M dwarfs. And the smallest possible star that you can have that still has enough pressure and temperature at its core is about 7.5% the mass of the sun. And just for comparison, that's about 75 to 80 times the mass of Jupiter. So in other words, if you, and to me, they're the same stuff as Jupiter. So if you could go and find another 75 Jupiters and crash them into Jupiter, which we don't have nearby, then you would create the smallest possible main sequence star, and that would be the smallest red dwarf star. And what's incredible about them is that they will live for 10 trillion years, that they actually consume their fuel a lot more slowly than the sun does. They're also fully convective. So the sun has these layers that it can only really pull in fuel from its core. It can't access a layer outside of that. But the small red dwarfs, they're fully convective. So they kind of mix themselves up all the time, and they're able to use up all of the material. So trillions of years from now, all that we'll see out there in the universe will be those small red dwarf stars. The smaller, the longer lived. How big are they? Red dwarfs can be 70,000 to 350,000 kilometers across. And you compare that to the sun, which is 1.5 million kilometers. So they're a lot smaller. Victor OE. I'm thinking about building a 150 millimeter f5 Dobsonian. Do you think that's a good idea? I live in Brazil and there are no cheap telescope options around here. Building a Dobsonian, if you have the time and the resources and the ability, is always a great idea. It is always the best idea, is that if you have the time on your hands, build a Dobsonian. Now, just to give a sense, 150 millimeters, that's like a 6-inch Dobsonian, I think. 200 millimeters is an 8-inch Dobsonian, and they get bigger from there. And so a 6-inch telescope is a great first starter telescope. And for those of you who don't know, a Dobsonian is the style of telescope that is very simple. It was developed by John Dobson, and it was sort of like the people's telescope. And what it is this tube with the mirror at the end of the tube, and then you have a secondary optics in the front, and then it's on this very simple alt-azimuth mount where the telescope can go up and down and turn left and right. And then you put a little finder scope on the side of that telescope, and then you can look into the sky. And if you're looking at an object, say the Jupiter, the moon, things like that, and you line it up, you can be able to see it. And a lot of the Dobsonian, you could buy Dobsonian telescopes, and they're relatively inexpensive compared to the other scopes that are on the market. They're called light buckets. And so if you're looking at some kind of telescope that's an 8-inch, say from Celestron, you might be looking at $1,200, $1,500. But a Dobsonian equivalent of that is going to be in the $300 to $500 range, depending on what country you live in. But you can build these telescopes yourself, and there are many great explainers on the internet on how to do that. We have one in our book about how to build one out of a stovepipe. So, if you have a tube that is about 6 inches across, 150 millimeters across, cardboard tube works. People have made them with metal tubes. You can also just have no tube at all. You could just have like an open framework, and then you put like black cloth around it, and that works as well to kind of keep the optics dark. And so to be able to build one yourself, you're going to want to find plans. And then what you need is either the mirror parts. So you can buy a sort of pre-ground reflective mirror that is the right size, as well as the secondary optics components. You can find suppliers on the internet for this. Often they're supplied out of China, and they're not that expensive. Like, you could probably put all the various parts of your telescope together for about $100, and then some basic woodworking to actually build the mount that holds the tube, that holds the mirror in place. But if you want to get even more sort of back to the basics, you can grind your own mirror. And so instead of you buying the pre-ground mirror with the reflective coating on it, you can buy a mirror blank, and it is literally just a disc of glass that you then have to grind down into the shape of the mirror. And so you can actually buy not only the blank, but then you can buy a template that you can use to sort of judge whether or not you've reached the right shape of the reflective mirror surface. And there are different kinds of shapes that you may want to build, but you have to sort of like grind with different levels of sandpaper and get yourself down to the point that you've got the nice shape. And then you can go and get the exterior of this mirror blank coated with some kind of reflective aluminum that then turns into your mirror. And so, if you have more time than money and you have a certain amount of technical acumen and you want to try and build something like this, it's an amazing project because it really teaches you from the ground up how a telescope works. And at the end of the day, a 150 millimeter chunk of glass, a 200 millimeter chunk of glass, they're not that much more expensive. And so most of the big amateur telescopes are Dobsonians that were made by hand. And there are some monsters. People have built 20-inch, 24-inch telescopes, right? This is a meter across. And, the bigger the mirror, the bigger the telescope has to be. And so a lot of these, the tubes are 3 meters long. People have to stand up on step stools to be able to look through the actual eyepiece. But they're light buckets. The amount of light that you can gather into this thing. There are nebulae, there are galaxies that you can only see if you do a long duration exposure with a telescope. But you look through one of these giant light buckets and you can actually start to see these features in real time. And of course, the planets look absolutely amazing. Now, the big downside of the Dobsonian telescope is that by default, you've got this alt-azimuth mount, and it is how good your woodworking skills are to be able to actually make this thing so it can go up and down and side to side. And that it's much more difficult to put it onto some kind of tracking mount. When you think about the sort of fancier telescopes that you can buy, they're often on an equatorial mount. So the telescope is turned to match the tilt of the Earth's axis, and that allows you to track for long periods of time. Often they have go-to capability where you have a little computer and you beep boop, point at the object that you want, and the telescope moves automatically and then tracks the target automatically. Those are a lot more difficult to build in, but not impossible. And so I think it's an amazing hobby. Like if you have like a mild interest in astronomy and you want to kind of go down this route, then seriously look on the internet, find some instructions to be able to build a Dobsonian telescope of your own, and then decide, do you want to build something that is a lot more, with a custom kit, with a kit, but then build some of the external elements, or do you want to go that next step and grind your own mirror? And there are going to be a lot of people that are watching this video right now who have gone through that entire process, ground your own mirror, your telescope is sitting there, and there's something to be said for having a telescope that you built with your own hands and that you're using to watch the sky. So is it a good idea? It's always a great idea if you have more time than money. It's time to shout out our new patrons at the $5 level and above. Daniel, Mesa Kevin, Billions and Billions of Stars, Philippe Pruot, Jason Claudianos, Victor Pomales, Kim Gunstick, Scott Cochran, and Alfonso Mazzarelli. Join the community at patreon.com/universe today. Daniel Redzic, what do you think of the possibility of black holes being created by accident by past civilizations experimenting with mass and pushing their limits? Well, we know how black holes can form, which is that we have a star with many more times the mass of the sun that implodes, and in this event, you get a black hole. And we see black holes that have been formed. We see stars that have had supernova with the amount of energy capable of producing a black hole. So, all of the bits and pieces for what it takes to make a black hole seem to be fairly obvious. Could advanced civilizations create black holes? Theoretically, sure. People have wondered if the Large Hadron Collider could create a black hole. We weren't able to do it, but it still seems theoretically possible that a future collider with more energy could produce a black hole. And once you've made a black hole, it's going to evaporate in a fraction of a second. But if black holes don't evaporate, then you've got a problem. You've created a black hole, and now what are you going to do with it? And it's going to fall into your planet and start to gobble up your planet from within. So, what I think the chances of this are very low. Black holes seem to form in natural ways, and there could be some out there that were created by civilizations, but it wouldn't account for the number and the mass of black holes. There are 100 million stellar mass black holes in the Milky Way. That there are, say, 2 trillion galaxies in the observable universe, each of which has a supermassive black hole with millions to billions of times the mass of the sun at the center of it. Those were probably just formed by stars crashing into each other, exploding, imploding, maybe large amounts of gas collecting into black holes. I can't see how people would be responsible for all that. PCAviator. Here's a question that I can't get a straight answer about. Do gas giants have a solid core? With all that pressure and gravity, would it compact anything so tightly at the center to become solid? It depends on what your definition of solid is. So inside Jupiter, down at the very core, there is probably 15 to 30 times the mass of the Earth in metal. And, metal is anything heavier than helium on the scale. So it is going to be oxygen and carbon and iron and all kinds of stuff. So that's down there inside Jupiter. And the pressure and the temperature are so high that hydrogen has been turned into a metal. They call this metallic hydrogen. And that this is what gives Jupiter its magnetic field. So it's really hard to explain. So if you had hydrogen that has a greater density than iron, is that solid to you? But yet it is moving around like a fluid that is creating a magnetic field. Is that still solid to you? So I think the reason you've been having a hard time getting a straight answer about this question is that what you're imagining is that Jupiter is this sort of big puffy cloud of gas, and that there's these cloud tops, and then there's this atmosphere, and you could fly around in it on an airplane, and then eventually you'd fly deep enough, and then there would be this ball in the middle where you could land. And obviously it would be high pressure and high temperature, but it would be sort of like something you can imagine. And that is not what's inside Jupiter. That what is inside Jupiter at the very top, like maybe the first 70 kilometers, is what you're imagining. The cloud tops and this light, fluffy gas and storms and hailstones of mush balls that are falling, and it's mostly ammonia. But then once you get down about 70 kilometers, then the density of the planet starts to take over. And you very quickly, within a few hundred kilometers depth, have hit a density that is like you're in the ocean, that you're in water. And the temperature is high. Temperature is already hundreds of degrees. And then you go down deeper, and now the pressure is like the bottom of the ocean. It is like the bottom of the atmosphere on Venus. And then you're still just a few hundred kilometers into Jupiter. And then you keep going. And now the density is like rock. And the temperature is entering thousands of degrees. And when you're at the center of Jupiter, the temperature is 90,000 Celsius. Like I said, hydrogen has been pressed so tightly that it is as hard as metal, is denser than metal, and that there is no point where this begins and ends, that it is this smooth transition from light fluffy clouds at the high atmosphere to hydrogen compressed into metal at the core with other various elements mixed in. And so, you have to imagine it's just this smooth gradient of increasing temperature and pressure. No place you could ever just land your spacecraft on. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call it Q&A Plus. This week's bonus question is all about what a fossil from Mars might be worth. All right, those are all the questions that we had this episode. Thank you, everybody who asked your questions in the YouTube comments, as well as everybody who showed up for the live show. Now, we record this show every Monday at 5 p.m. somewhere in the world. So it's a really good time. It's 2 hours long, lots of questions, lots of back and forth. It is 2 hours. So definitely, if you want more questions, definitely come and join us for that. I'm going to talk about some media, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bear Lake Roofing, Brian Body, Carolyn, Chuck Hawkins, Commander Baylock, Cy Nelson, David Gilson, David Matz, Dustin Cable, Evan Pro, Greg Feely, Hunt Schultz, Hudson Ward, Jay Graves, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Marcel Smits, Michael Purcell, Modzo, Paul Robach, Rank Haidu, Robeck, Sean Sargent, Stephen Fonlamunley, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So it's a very good time for media, and I have been taking advantage of this, and I want to let you know about a bunch of the stuff that I've been watching and playing. So first, watching. Now, of course, I've been watching Andor, and at the time that I'm recording this, we've had 2 weeks of Andor, 6 episodes so far, and they are so good. as good as the first season. And so if you haven't watched Andor yet on Disney, this is the Star Wars telling of the leading up to the rebellion. And it's the best piece of Star Wars ever created. Better than Star Wars. So definitely check that out. And most Star Wars, I'm like really sick of it, but I can't get enough Andor. Next up, there's a pretty cool series on Netflix called Eternaut. And it is about this weird snow that falls in Buenos Aires in Argentina that kills when it touches you. And so people die, but then other people figure out how to deal with the situation. And then as they do, things get weirder. And so far, my wife and I have been completely hooked. We've been watching. We're only 2 episodes into it. And so I don't know how this ends yet, but I can highly recommend those first 2 episodes. And so if you're looking for something science fiction-y, but like out of left field, definitely check out Eternaut. It's like eternal astronaut, Eternaut. And then last up, I have been playing the game FTL. And I can't believe it took me this long to play this game. You sort of like Captain Picard running the Enterprise, but you are running this starship and you're figuring out which improvements and upgrades to make. And then you deal with various pirates and rebels and slave traders, and you're trying to get your spacecraft through all of these different hostile areas. And the game is so good. And very old, like it's 12 years old, and yet it's easily one of the best games I've ever played. So if you've never played FTL, definitely check that out. All right, that was some the media that I've been enjoying. Hopefully you will play or watch a bunch of this as well. All right, we'll see you next time.